Hello. We are going to start a new chapter. Chapter 11 is about regression with a binary dependent variable. So now, as you can see, this chapter is about the dependent variable. So far, we have not studied what happens if the dependent variable y, the left-hand side variable, changes. So this chapter is a study about the dependent variable. So these are brief outline. Let me skip that. So as I said, so far the dependent variable did not receive much attention. So because it's natural. So like examples are average test score, traffic fatalities. Those are our example dependent variables, and they are continuous. We say a variable or random variable is continuous if it can take an arbitrary number like 0.1, like 1, 2, 3, 4, or 0.1, 0.2, 0.0001, 0.99999. So there are continuously many possible values in those two cases, right? So it's a real number, but we are going to consider a more limited dependent variable. So the most common form is the binary random variable. Say y is binary in these cases. For example, y is 1 if a person gets into college, and 0 if not. And we would like to explain the admission decision using high school grades, SAT scores, demographic variables. And in the second example, we would like to explain what kind of people tend to smoke. The smoking decision is what we would like to explain. So then y takes 1 if a person smokes, and 0 if not. And it is explained by tax rate, income, demographic variables. Like for example, so we would like to study how much smoking will be reduced if cigarette tax rate increases. So that's an interesting policy question, and you may use these kind of data. And in third example, y is the mortgage application decision. So 1 if accepted, 0 if rejected. So it is acceptance or rejection. So it's another 1 or 0 decision. And it is explained by race, income, house characteristics, and marital status, and many other economic status and like social status variables. And as you can see, our focus is now on the dependent variable, y. Y is the dependent variable, what we try to explain, and the dependent variable depends on x, so determined according to x. So, and in those three examples, the common common structure is that y has only two possible cases: getting admitted to college or not, smokes or not, and accepted or rejected. So this kind of random variable is called binary, a binary random variable. A more concrete example is Boston mortgage data. So in a real data set, we observe 1990 mortgage applications in Boston area. So we have more than 2,300 observations, 2,300 mortgage applications, and we observe whether their application is denied or not, denied or accepted, and we observe the applicant's income, employment status. Income and wealth. Income is like annual income, and wealth is how much you have in your savings account or in your stocks, and so cumulative income is wealth. and other loan status and property characteristics, race of applicant. So it is a very interesting question. What is the main determinants of mortgage application acceptance or denial, and like how much the income affects, or what is the relationship between the other loan status and mortgage application, or if there is any racial discrimination in the mortgage decision or not. So it's an interesting question, and you may approach to this question from many different social sciences, economics and sociology and other things. Anyhow, this is our running example. We are going to use this example throughout this chapter. So now then, let's think about the standard, the regular linear regression model that we considered earlier. Like say, y, the mortgage application result, is determined by x, beta 0 plus beta 1 x plus error term. So in this simple linear regression model, we interpreted beta 0 as the intercept. So beta 0 is the value of y, predicted value of y when x equals to 0. And beta 1 is the slope, which is the amount y increases when x increases by 1 unit. So beta 0 and beta 1 have their own interpretation and their meanings. And if you obtain beta 0 and beta 1 as a result of the OLS estimation, then you can predict the y, outcome y, using these two values. Then for example, suppose that you predicted the mortgage application result using, say, income, a household's income. Then you obtain 0.26. What does that mean? So this is the first problem, the major problem in handling binary variable. So remember, the binary variable has only two values, acceptance or denial. And usually suppose that acceptance is encoded as 1 and denial is encoded as 0. So it's 0, 1, 0, 1 data. And so y can take only two possible numbers, 0 and 1. But your predicted value is not one of them. Your prediction is 0.26. It's neither denial nor acceptance. Then you have to change your interpretation. The idea is, we call this linear probability model. We are going to call this linear probability model because we have to interpret the result like 0.26 as the probability, because there is nothing in between 0 and 1, but you obtain some number, you may obtain something between them. Then you cannot explain what is the result, but then the idea is you have to explain 0.26 as the probability of acceptance, the probability that your applicant is accepted, given conditional on the income. Mathematically, you can calculate that. So originally, we interpreted the predicted value as a conditional expectation. So conditional on your income x, what is the expected outcome? This was how I introduced the linear regression model in an earlier chapter. That is right, but now it is not natural. You cannot explain 0.26 acceptance. That does not exist. So, and by a simple math, because y can take either 1 or 0, so its expectation is like say given x, probability that y equals to 1 is this much, then y will be 1. And probability of 0 is this much, and the outcome is 0. did I say 0? So probability of 0 is this much, and you multiply the outcome 0. Then anyhow 0 goes away, you only have the probability of acceptance. So the expected value of y equals to probability of 1. Then what is good about this here is when you interpret the outcome as a probability, but you may apply all the techniques, all the statistical methods that can be applicable to the conditional mean. So you can take advantage of all the properties of mean, but just interpret as a probability. So it's actually nice. It's I introduced as if it's a problem, but actually it's a nice property. You may choose whatever you like, and if you need a mean, then you may apply the methods and then interpret as a probability. Then in the end, so simply speaking, in conclusion, we are estimating the probability that you are accepted, your application is accepted, given your income. And this probability is simplified to a linear function of x. So beta 0 must be interpreted as the probability of acceptance if your income is 0. Of course, it's unrealistic. No one has income exactly at 0, but just mathematically, you have to calculate that. And beta 1 is the beta 1 means how much the probability of acceptance increases when your income increases by $1 if x is measured in dollars. So if x increases by 1 unit, your probability increases by beta 1. So this is called the linear probability model because the probability is a linear function. Then, as I said, I already explained everything. So then your predicted value is the predicted probability. It's not that is the best. That is how we interpret the prediction, the result. And beta 1 is exactly how much probability increases when x increases by 1 unit. That is how we interpret a binary regression model. Interpret a model with binary dependent variable. So here is an example. Say you observe, principal income ratio, maybe PI, payment and income ratio. So among your income, how much you have to pay each month. Like for example, if I earn $1,000 every month, but I have to pay, say $500 as a mortgage payment, then my PI ratio would be 0.5. So as your income increases, PI ratio will go down. But if your payment increases, your PI ratio will go up. So as it goes to as the PI ratio increases, your bank will your application will be more likely to be rejected. So that is predicted by the linear probability model. So your observation is here. So they are 0. Their outcome is 0. And in this case, by the way, in this data, y equals 1 if denied, and y equals 0 if accepted. Does not matter. You may change 1 or 0. It's just a matter of how you encode 0 or 1, and then so like the accepted approved mortgage applications are on the lower side of PI ratio. As I said, lower side means they are more likely to pay regularly, less likely to go bankrupt, and denied applications are more likely to be on the higher side of PI ratio. Their payment takes a more larger part of their income. So you estimate a probability by a line. This is the best fitting line. And then, for example, if your PI ratio is 0.4, I heard that many banks use 0.4 as a threshold. So if your PI ratio is greater than 0.4, then usually you are rejected. And 0.4 has a probability somewhere here, which is, I'm not so sure, but say 0.45, just assume that if your PI ratio is 0.4, the estimated value is 0.45, then you have to interpret 0.45 as the probability of denial. Because 1 stands for denial, right? So it is probability of y equals to 1, which means denial. So you are estimating the probability of probability that your application is denied. Okay, this was a brief introduction, and I will continue in the next video. Bye. See you later.